we'll get that started. So negative 23.5 for number 1 for x. Number 2 is also going to be slightly regrouping. 4 is 2 squared. So that'll be 2 squared to the power of 3x minus 4. Or 2 to the power of 6x minus 8. 512 then is 2 to the power of 9. So this becomes 6x minus 8 equals 9. And we solve by adding 8. 6x equals 17. And dividing by 6. X equals 2 5/6. Any questions there? Okay. Finally, number 3. This is one that requires you to remember the formula from yesterday for half-life. A sample of 500 grams has a 9-year half-life. How much would remain after 20 years? So the amount that remains is equal to that initial amount, 500 grams, times 1/2 to the power of our time, 20 years, over our half-life of 9 years. So this is just a calculator problem. 500 times 1/2 to the power of. It's safest to put that power in parentheses since we have to do an operation in it. 20 divided by 9 and close that parentheses. We get 107.15. And that'll be grams of material left after 20 years. Any questions on any of those? Any questions off the homework from yesterday? Okay. So yesterday was dealing with exponentials. Today we're looking at the other side of the coin, the inverse of it, called logarithms. And before we get into logarithms, I want to talk about that concept of inverses. So far we have encountered several inverses in this course and in other courses you've had. I mean, the simplest one is addition and subtraction. If I start out with a number, x plus, and I add something to it, x plus 7, the inverse of that is to subtract 7, gets me back to just x. Or on the other side, if I had x minus a number, x minus 3, if I add 3, it gets me back to just x. Adding and subtracting the same number puts you right back where you started. They cancel each other out. They invert each other. Multiplication and division. If I have 5 times x, I get back to x by dividing by 5. If I had x divided by 3, I get back to x by multiplying by 3. Cancels those out. So those are the simple, obvious inverses that we started with. Other ones that we've seen have been powers and roots. If I have, let's just use a number in here, 5 to the power of 7. If I want to get that back to just 5, I do the 7th root. If I have the 4th root of 29, if I want to get that back to just 29, I do the 4th power. Roots and powers cancel each other out as long as the power is the same as the index. We haven't explored it in this course, but outside of this course, you might have seen trig functions and their inverses. If you have, the sine of 30 degrees is 0.5. Well, the inverse sine of 0.5 gets you back to 30 degrees. There's inverses in trig functions. Well, yesterday we talked about exponentials. And the difference between exponentials and an exponent is typically x to the power of a number. x to the power of 4. We could reverse that by simply doing the appropriate root, the fourth root. Reverses the power of 4. In exponential, the variable is not what we were acting on. The variable is what was doing the action. It wasn't x to the power of 4. It was 4 to the power of x. To reverse that, today we're going to talk about logarithms. And a logarithm is the opposite of an exponential. Doing the logarithm, the appropriate logarithm on that 4 to the power of x, is going to give us back just x. So the difference between our powers and roots is a root, when we used a root on an exponent, it canceled out the power and brought us back to whatever the base of that exponent was. When we use a logarithm on an exponent, it's going to cancel out the base of the exponent and give us back whatever the power of that exponent was. So let's do a definition of a log. Log base A of B equals, let's go C. What that is telling me, first of all, A is the base of the log. That is significant. Remember when we had an exponent, we had x to the power of y, x was called the base of the exponent. Y was called the power. They're both called the base for a very good reason, because they have a very close link. So that base of A, if you put it in the related exponential form, is the base of that exponent. What this is saying, log base A of B, is saying A to the power equals C, is saying A to the power of C equals B. So what does that mean? Well, log base 3 of 9 would equal 2. Why does that equal 2? Because the base of the log, which is 3, to the power of 2 equals 9. So if I ask you, what does log base 2 of 32 equal? What that's asking is 2, I'll put an x in there, solve for x. That's saying 2 to what power equals 32? Well, 2 to what power would be 32? 5, very good. So log base 2 of 32 is 5, because 2 to the power of 5 equals 32. So in your notes, I want you to try to find for me log base 4 of 256. What'd you get? 4, very good. Log base 4 of 256 is asking 4 to what power is 256? And it comes out 4 to the 4th power is 256. This here is what's referred to as the logarithmic form. This is what's referred to as exponential form. It is rather useful to be able to switch fairly quickly, fairly conveniently between the two. If I say log base 5 of 125 equals 3, what would be the corresponding exponential form? What would be the base of our exponent? Careful. The base of the log is the base of the exponent. So log base 5 means it's 5 to the power of. What is going to be the power of our exponent? The 3. So remember, the base of the log becomes the base of the exponent. The result of the log is the power of the exponent. And of course, the object of the log is the answer in the exponential form. If I wanted to go the other direction, if I had 3 to the power of 6 equals 729, that's exponential form. If I want to convert that back to logarithmic form, what is the base of my log going to be here? The 3, very good. The base of the exponent is the base of the log. What's the object of my log going to be? The 729. The result of the exponential is the object of the log. And of course, over here would be the 6. The power becomes the result of the log. In your notes, I want you to convert this top one, log base 7 of 2,401 equals 4, convert that into exponential. And then the exponential, 5 to the power of 6 equals 15,625, convert that into logarithmic form. And I'll give you a minute. So log base 7 of 2,401 equals 4. What's that going to become in exponential form? 7 to the power of 4 equals, perfect, 2,401. Going the other way, 5 to the power of 6 equals 15,625. What's that become in logarithmic form?
Log 5, 15,625 equals 6.
Perfect. Log base 5 of 15,625 equals 6. Beautiful. So the relationship between these logs and our exponents, obviously it deals with this base here, right? If they have the same base, if the base of the log is the base of the exponent, which is what we saw up here, the base of the log was the base of the corresponding exponent, then they are related. They are actually inverses. Log base 2 and 2 to the power of are inverses. So log base 2 of x and 2 to the power of x would be considered inverses. So what does that mean? That means if I do a log base 2 of 2 to the power of x, the base of the log and the base of the exponent will cancel each other out, and that's going to give me just x, or whatever the power is there. If I have log base 11 of 11 to the power of 3x minus 2, the log base 11 and the 11 to the power of, the 11 in the base of the exponent, cancel out again. That gives me just 3x minus 2. Well, as we saw with our other inverses, it goes both ways. Subtraction can reverse addition, but addition can also reverse subtraction. And the same is true here. The log can reverse the base of the exponential, but an exponential with the appropriate base can reverse a log. If I have 5 to the power of x in log base 5 of x, just like up here, I put that 2 to the x in where the x was so they would cancel out. Here I want to put the log base 5 of x in where the x is. So instead of 5 to the power of x, it's going to be 5 to the power of log base 5 of x. Just like before, the base of 5 in our exponent and the log base 5 cancel out, and this just equals x. I might have 23 to the power of log base 23 of 7x plus 13. The 23 and the log base 23 to the power of and log base 23 will cancel out. And again, that is just 7x plus 13. I'd have you practice some of those in your notes, but it's really just pretty simple, rewriting whatever that power is, or the, oops, get out of here. So the next step is to look at some basic logarithmic equations. The simplest ones look like this. Log base 3 of x equals 5. And in many cases, solving a simple logarithmic equation is simplest if we just turn it into this exponential form. The exponential form of this is 3 to the power of 5 equals x. Well, now we know that x is found by simply doing 3 to the power of 5. Which, of course, is 243. Or if we have log base x of 64 equals 6. Well, the equivalent exponential form is x to the power of 6 equals 64. Well, what to the power of 6 equals 64? Two to the power of 6 equals 64. So x equals 2. In your notes, I want you to solve log base 5 of x equals 3,125, and log base x of 343 equals 3. Solve those quick. So the first one, that would be rewritten as, oops, I did that way backwards into 5 to the power of 3,125 equals x, which is going to be a number that's way off the screen of your calculator, right? It's going to be exponential or scientific notation. Number 2 would be rewritten as x to the power of 3 equals 343. What does x become there? If you try it, 7 to the power of 3 is 343. So x has to equal 7. A little bit trickier than those two basic forms would be something like log base 3 of 81 equals x. So this is asking us now, 3 to the power of x equals 81. And again, at this point, it's a matter of trial and error. What can you put in there for x that 3 to that power will be 81? Well, if we try it, 3 to the power of 4 equals 81. So we get x equals 4. I want you in your notes to try this one. Log base 17 of 1 equals x. So the equivalent exponential form here is 17 to the power of x equals 1. 17 to what power equals 1? Well, anything to this power equals 1. It is 0. X to the power of 0. 17 to the power of 0 equals 1. I know, I sometimes think I'm funny. If log base 3 of 81 equals, we said x had to be 4 there, right? then log base 3 of 1 over 81 is very predictable. It has to be negative 4. Remember, this is saying 3 to the power of 4 equals 81. This is saying 3 to the power of negative 4 equals 1 over 81. A negative power is a reciprocal. So if we know the log of a number, we know the log of its reciprocal. Log base 5 of 3,125. That's saying 5 equals x, of course. It's saying 5 to the power of x is 3,125. Well, x ends up equaling 5. Once we know that, what's log base 5 of 1 over 3,125? What's that have to be? Negative 5. Perfect. Log base 10 of 100,000. Log base 10 is actually fairly simple when you have even numbers like this, 100,000, because 10 to what power equals 100,000? You got it. There's 5 zeros, so that's 10 to the 5th power. So log base 10 of 100,000 is 5. So then how would I do log base 10 of 0.001? Well, I'm going to rewrite that. 0.001 is 1/1000th. Log base 10 of 1,000 would be 3, right? So log base 10 of 1/1000th would be negative 3. Perfect. So I know I should actually, let's do this one first. Log base 5 of 1, of course, we said is, that's saying 5 to what power equals 1? What does x have to be? 1. Careful. 0. 5 to the power of 0 equals 1. So if I give you an equation, log base x of 1 equals 0, that's saying x to the power of 0 equals 1. Can I solve that for x? I cannot. This is indeterminate, like many of our systems of equations were, or our linear equations where the variables disappeared. X here can be any number, because anything to the power of 0 is going to give us back the 1. Log base 9 of 9 is going to be what? What's x have to be there? Well, 9 to what power equals 9? Be brave. It's 9 to the power of 1, right? Anything to the power of 1 is itself. it gets kind of confusing because you think what the ones do and the zeros do with the powers kind of overlap in what your thought process is. But log base x of x is always 1. If the base of the log and the object of the log are the same, the result is always going to be 1. And as we saw earlier, log base x of a to the power of x, what's that going to equal? Oops, sorry. Let me, log base x of x to the power of a, what's that going to equal? A, yes. The log base x and the base of x in the exponent cancel out. And the other side of that was x to the power of log base x of a is going to equal a. Again, the base of x in the exponent and the log base x cancel out, no matter what order they're in. Log base 1 of x equals y. What this is asking us is 1 to the power of y equals x. What is the only possible value of x here? Doesn't matter what y is. X has to be what? One. Because 1 to any power is going to be 1. I can multiply as many 1s together as I want to. The answer is still going to be 1. So we really cannot have a log with a base of 1. It doesn't work. So that base of that log either has to be bigger than 1, or what happens if the base of the log is a decimal? Log base 0.2 of 0.008 equals x. Well, this actually does work. This is saying 0.2 to what power equals 0.008. If you take 0.2 to the power of 3, you get 0.008. So x here is 3. You'll notice, however, when that base of the log is less than 1, these numbers here have to be really small. They're smaller than the base. So let's explore that base a little bit. Oh, excuse me. Log base a of x. If a is greater than 1, x has to be bigger than a. Or, if x is bigger than a, the result is positive. Or if x is less than a, the result is negative. If a is between 0 and 1, note we said that a cannot equal 1. It just doesn't work. If a is between 0 and 1, the opposite is true. If x is less than a, then the result is positive. If x is greater than a, then we have a negative result. Well, these logarithms allow us to combine some kind of interesting, some large numbers, or combine the logs themselves, do the operations with the logs in kind of interesting ways. Let's start out with log base 2, just because most of us are relatively familiar with the powers of 2, so we can work with them fairly quickly. Log base 2 of 8 times 4. I'm going to start out doing this the long way. 8 times 4, of course, is 32. Log base 2 of 32 is 5, because 2 to the power of 5 equals 32. But rather than multiplying the 8 times 4, we could split that up. Log base 2 of 8 and log base 2 of 4. Log base 2 of 8 is 3. 2 to the power of 3 equals 8. What's log base 2 of 4? 2. 2 to the power of 2 equals 4. If I add 3 plus 2, I get 5. One of our rules for combining logarithms is log base x of a times b is equal to log base x of a plus log base x of b. I might have log base 2 of 64 divided by 4. Again, if I just go about this brute force, I divide out 64 divided by 4 is 16. And we know that log base 2 of 16 is 4, because 2 to the 4th power is 16. But what if I do log base 2 of 64 and log base 2 of 4? What's log base 2 of 64?
Yes.
6. 2 to the power of 6 is 64. Log base 2 of 4, of course, is 2. If I subtract those, I get the result I had from the division. Giving us our second rule for combining logarithms. Log base x of a divided by b is equal to log base x of a minus log base x of b. How about log base 2 of 4 to the 5th power? Well, again, we could do it brute force. 4 to the 5th power is 1,024. If you work through that, 2 to the power of 10 is 1,024. So log base 2 of 1,024 is 10. But what is log base 2 of 4 is 2 still, right? If I multiply by that exponent of 5, I get the 10. So our third rule of exponents is log base x of a to the power of b is equal to b times log base x of a. So if I have log base 3 of 81 to the 5th power, I can make that 5 times log base 3 of 81. Much easier to do log base 3 of 81 than it is to try to do 81 to the 5th power. What is log base 3 of 81? 4, good. So 5 times 4 is 20. Log base 3 of 81 to the 5th power is 20. Log base 5 of 15,625 divided by 125 can be written as log base 5 of 15,625 minus log base 5 of 125. Now I realize these problems look a lot simpler like this if you have your powers memorized. I've used them enough that I can pick them out pretty quickly. Log base 5 of 15,625 is 6. 5 to the power of 6 is 15,625. What is log base 5 of 125? 3. So 6 minus 3 is 3. So log base 5 of 15,625 divided by 125 is 3. That one's a lot less useful than this other one. Back to our first one. Log base 7 of 49 times 343 can be split into log base 7 of 49 plus log base 7 of 343. What's log base 7 of 49? 2. Log base 7 of 343? 3. So 2 plus 3 is 5. So log base 7 of 49 times 343 is 5. Now obviously for calculations, we have the calculator. There's no reason not to just do 49 times 343 or 15,625 divided by 125. We have the calculator. We can do that rather quickly. It's when we throw variables in here that it's handy to be able to break them down. For example, the log of, well, let's do log base 7 of, oh, where am I? There we go. X squared over x minus 7. I can separate that into what two independent logs? Actually, 3 independent logs here. Well, it'll be 2, but I'll have to do 3 adjustments. First will be log base 7 of x squared, plus or minus here? Minus, because we're dividing. Minus the log base 7 of x minus 7. That's what we're dividing by. Now there's one more thing I can do here to break down this log. Do you see what it is? That power. Log base 7 of x squared is 2 times log base 7 of x. So log base 7 of x squared over x minus 7 can be broken down into 2 times the log base 7 of x minus the log base 7 of x minus 7. I can use these rules. Well, let me have you guys try one here. Let's do log base 3 of 4x over 2 minus x squared. I'm going to give you a minute to break that one down. So this is log base 3 of 4x, the numerator, plus or minus. We are dividing again, so it's minus. Log base 3 of 2 minus x squared. Can I do anything with that 2 minus x squared? Why not? The squared is not on the whole thing. If this had been log base 3 of 4x over 2 minus x squared like that, then we could have. This would have first split into log base 3 of 4x minus log base 3 of 2 minus x squared. Then we could have done that exponent. Since it's on the whole object of the log, then we can bring that out front. So the log base 3 of 4x isn't going to change. This will be minus 2 times the log base 3 of 2 minus x. So that power has to be on the whole object of the log, like it is here, not just on one piece of it like it is up here. We can go the other way. We can use those rules to recombine things. We might have log base 11 of 9 minus 2 times log base 11 of x. I can recombine here. First thing I see is the log is multiplied by a number. That number multiplying the log can become an exponent of the object. So the log base 11 of 9 up front here, I'm not going to change, minus, this is going to become log base 11 of x squared. I'm reversing that process. Instead of taking the exponent out and putting it up front, I'm taking the multiplier up front and putting it back in an exponent. Now, before we took division and we broke it into subtraction, now we're going to go the other way. We have subtraction of two logs. We're going to pull it back to be division. So log base 11, the 9 goes on top, subtracting the log of x squared, so the x squared goes on bottom. So that all can be combined to be log base 11 of 9 over x squared. Now the base of the log, the base 11, is just arbitrary. I threw whatever number I wanted to in there. But just know that it has to be the same base on the log throughout the whole problem. If I had log base 5 of 3 plus log base 5 of x, I can combine that to be log base 5. Remember, addition was the breakdown of multiplication, so 3 times x. However, if it was log base 4 of 7 plus log base 5 of x, why can I not combine those? Yes, they're not the same log. Different bases on the log. One's a log base 4, the other's a log base 5. In your notes, I'm going to have you combine this one for me. 4 times the log base 3 of x plus 2 times log base 3 of y. I'll give you a minute to combine those. So 4 log base 3 of x become log base 3 of x to the power of 4. 2 log base 3 of y will become log base 3 of y squared. And then the plus is from multiplication, so that's log base 3 of x to the 4th y squared. Any questions? So at this point, you might be thinking, well, that is great, but I don't have a log base 3 or log base 5 or log base 7 button on my calculator. And your calculator doesn't have the option in most cases to enter alternative logs. Your calculator has 2 buttons, log and ln. The log key is log base 10. In fact, whenever you see log 100 with no base written there, it's assumed, if there is no base written there, it's assumed that that's a log base 10. Of course, log base 10 of 100 is 2. ln, in order to define ln, natural log, we have to define a number called e. E is what is referred to as the natural constant. E actually occurs in nature a lot. That's why it's called the natural constant. The growth of bacteria colonies seems to go up by factors of E. Continuous compounded interest goes up by factors of E. In fact, any continuous growth rate problem goes up by factors of E. It's one of those things where they discovered that number in one setting, And after that, they kept discovering that same number over and over again in different places. Anything really that deals with growth and decay, in many cases, it involves that factor of E. And E, oops, let me clear that out. I actually need to do second. The number E is 2.718281828, and it goes on forever. It does not keep going 18281828. It gets out of that pattern. Typically, we round E as 2.183. Oops, sorry, 2.7183 for E. So ln of E is a log base E. The reason we use that, the reason we have a special log for it, like I said, is E tends to come into play so often. Continuously compounded interest. We looked a little bit at annually compounded interest yesterday. Continuously compounded interest, the balance is equal to the principal times E to the power of the rate times time. So if I invest $1,000 at 8% for 5 years, that would give me a balance of 1,000 times E to the power of 0.08 times 5. $1,491.82. Now, I don't expect you at this point to necessarily know the keystrokes on your calculator to calculate that out, but you can see that's a pretty handy calculation. Well, anytime we're going to use an exponential like this, E is the base of an exponential, to do a calculation, there's going to be times when we want to reverse it. So to reverse it, we need a log base E. And that exponential with E as the base, and it comes up, like I said, in compound interest, bacterial growth, charging of capacitors in electronics, movement of current through an inductor in electronics. It's all over the place. So it occurs often enough that if we wanted to solve those equations, we need the logarithm to do it. So log base E, or natural log, has become kind of a staple in our calculations. So we can use those buttons on your calculator. If you have your calculator with, find the log button. Most of the time your calculator puts it in capital letters. We can approximate log, of course you know that's log base 10. I'm not going to, whenever it's log base 10, I'm not going to write in a base from now on. But log of 200. Did you get 2.301? You got it. Log 200. You don't have to close the parentheses, but it's good practice to get into. 2.301. Have you guys try to beat me to this one? Log of 4,000. 3.602? How am I able to do that so quickly? Well, one, I'm a geek. Two, I've done this crap a lot for a lot of years. But there's patterns. Math is about patterns. There's patterns everywhere in math. And this is one of them, a log base 10. Let's do log base 10 of 50. What do you get? Do you get 1.699? How about log base 10 of 25? 1.398? If I subtract those two, the difference is 0.301. That doesn't seem significant quite yet. But let me do log base 10 of 12.5. You get 1.097. What's the difference between those two? .301. In log base 10, if you cut the number in half, the log goes down by 0.301. So let's say I wanted to find the log base 10 of 5,000. Well, I know that log base 10 of 10,000 is 4. Log base 10 of 5,000 is 3.699. I just subtract 0.301 from 4 because 5,000 is half of 10,000. You can double check that on your calculator if you want to. If it's double, the log goes up by 0.301. If I want to find the log of 20,000, well, log of 10,000 is 4. Log of 20,000, I add the 0.301. This makes for some really interesting quirks in logarithms. If I tell you that log base 10 of x is 17.2 and log base 10 of y is 17.802. I actually totally have defined the relationship between x and y right now. The difference between those logs, 17.802 minus 17.2 is 0.602. That is 0.301 times 2, right? What that means is to get from x to y, it is doubled twice. So y is equal to x times 2 again. Or in other words, y equals 4x. Oops. If I know that log base 10 of 100,000 equals what? 5. Very good. Log base 10 of 800,000 to get from 100,000 to 800,000. Let me do this. 100,000, of course, is equal to 5. Log of 100,000 is 5. If I double 100,000, what do I get? 200,000, right? Log of 200,000 has to go up by 0.301. So log of 200,000 is 5.301 because it doubled. If I double 200,000, what do I get? 400,000. This has to go up by how much? The log has to go up by how much? 0.301. So that's 5.602. If I double 400,000, I get 800,000. The log has to go up by 0.301. So therefore I know the log of 800,000 is 5.903. That pattern of the doubling and halving is not going to be in the homework today, but it's something that is significant. If you work in electronics at all and do signal testing, it's a huge deal if your signal goes from 47 decibels, decibels is a logarithmic scale, to 47.3 decibels. That doesn't seem like a big deal, but guess what? Going up by 0.3 is doubling the strength. So from 47 to 47.3, you've doubled your signal strength. Okay, you guys have suffered enough for the day. Homework 15B covers the material that we discussed in class today. Anybody have any questions? Okay, well, you guys have a great day, and we'll see you all tomorrow.